This coil of wire is known as an air core solenoid. It's 500 to 600 turns of painted magnet wire, which is insulated from itself, wrapped around a hollow core. And we can pass a current through the coil, creating a magnetic field, both in the tube and on either end of it. So let's do that. You can see right now the two compass needles are pointing towards geographic north, but that changes rapidly when I hook the battery in. Now we have the magnetic field coming in here as if it's the south pole of a magnet, and going out here as if it's the north pole of a magnet. So inside, the magnetic field lines will be running in this direction. We can simply reverse the direction of the magnetic field by reversing the direction of the current. So let's do that. We should see the needles right now, they're going back to geographic north. We should see them go the other way. So now this is like a north pole here, and this is like a south pole. We're going to use this coil and the uniform magnetic field it creates inside to put a force on moving charged particles, in our case electrons. We're going to use this to investigate the direction of that force, and also maybe something about those charged particles.
The purpose of this lab is going to be to put a magnetic force on moving electrons. Now in order to do that, you need a source of moving electrons. And it turns out in the past, a lot more consumer products actually worked by sending beams of electrons to specific places. This vacuum tube, which was used in an old radio, is one such device. And the PSSC physics program, they're the folks who made all those old black and white movies I like showing in class so much. They developed a lab where they took this vacuum tube and they put it inside one of these air core solenoids, these coils of wire. And when you pass a current through these coils of wire, you create a magnetic field. So with the magnetic field created in a solenoid and with the beams of electrons in this tube, we actually can see how they interact with each other. Let's take a closer look at the tube, and then we'll look at the solenoid.
I'm sitting here with this cool device called a Magic Eye vacuum tube. And it was used way back in the day with old radios in order to see how in tune they were, or if you needed to fiddle with the dial to get the station a little bit better. The tube is hooked up to something equally interesting looking, this rather scary setup of 24 9-volt batteries, which at the moment is giving about 235 volts.
To generate the type of electric field you need to direct beams of electrons around, you need a very high potential difference. This tube was rated at 250 volts. Now I didn't have any power supply that could deliver that type of potential difference, so I built kind of a scary one. I went and bought a whole bunch of 9-volt batteries, and I daisy-chained them in series. So the negative of this voltmeter and the circuit is hooked up to the negative of this battery. Its positive is then hooked up to the negative of another battery, and so forth. All these are in series until we get to the positive side, which is hooked up to the external circuit. So that got me about 236, 237 volts. This is not a particularly safe thing to do. I knew that the vacuum tube I was going to use was going to draw very little current, so I wasn't too worried about an explosion. But 237 volts will generate a very large current hooked up to most electronics like we'd see in class. And that current might be enough to cause these batteries to explode. So I don't recommend doing this. It's on an asbestos fireproof table. There were no students around. And it got the job done, but it still scares me a little bit that I did it. So don't do it yourself.
It's easier to see what's going on if you look at the tube from the side. This is what people on their old radio would have seen when they looked at it. But let's zoom in on the side of it. In addition to the glowing top, I hope you guys can see a glowing red piece of wire. And that's just red hot. That's not doing anything particularly interesting. It's actually acting like the filament in an old light bulb. In fact, it's not plugged into the 235 volt battery. It's plugged into the lab power supply. It's getting about 6.3 volts right now. Just like an old light bulb, that electricity makes a wire glow and give off light.
So that heater heated this part in the middle, which is called the cathode, and it gave off cathode rays, or beams of electrons. Now the point of that huge potential difference was to create an electric field between the middle part, the cathode, and the outer part, the anode. And that's going to make electrons move. Let's look at how they move in this electric field.
So we want electrons to leave the central electrode and move towards the outer one. And we're going to do that by putting the large potential difference, 236 volts, across the two electrodes. That's roughly going to make an electric field going out of the positive and towards the negative. It won't have exactly that shape, but that will make our electrons obtain a velocity against the electric field. So that's the point of the high potential difference. In the middle, the electrons are being created, and then they're being pulled to the outside. They're being pulled in every direction where you see the glowing, but it's always along the top of the tube, kind of outwards in that circle. And what they're hitting contains a special chemical, and that chemical, when it gets hit with electrons, it glows and it gives off light. So what's our best way of finding equations that can help us understand the behavior of the electron? We should start with the basic physics we know, things like Newton's second law and conservation of energy. So we've got electrons that are leaving this location. They're being attracted because of the potential difference between these two plates. That means their potential energy is changing. So conservation of energy seems like a logical equation to use. So an electron's going to start here in the middle. It's got potential energy there. It's going to finish here on the outside on the positive plate. All its potential energy will have been converted to kinetic. So we'll just plug in the equations for electrostatic potential energy and kinetic energy. And we see that after doing this, we have an equation that we know most of the things from, but there's two things we don't know. We don't know the mass of our electron, and we don't know the velocity of our electron. So what we're going to do is apply a second field, a magnetic field, and hopefully we'll find another equation that has these two variables in it too. So in a moment, you're going to see me put the coil of wire over the tube. You're going to see how I'm going to control the magnetic field in that coil of wire. We're going to be able to make a magnetic field that goes straight down in this coil of wire. And that's going to put that force on those electrons and make them start spinning. And we're going to be able to measure it. All right, so I have our same picture of the electrons moving from the center negative to the outer positive. I've erased the electric field because we really just care about the velocity, the direction the electrons are moving. We are going to be applying with our solenoid a magnetic field in the downward direction. And I want to predict what direction the force ought to be on these moving electrons. So we do that with the right-hand rule. Remember, your thumb is the force, your index finger is the direction of motion, the velocity, the magnetic field is your other fingers. So pointing in the direction it's moving, curling my wrist so my other fingers are pointing in the direction of the field, a positive particle would have a force outward. It would start accelerating towards the camera. Of course, electrons are negative, so we expect a force inward. These electrons ought to accelerate away from the camera. So we can symbolize the force like that. But the thing that's glowing is shaped like a cone. It's like an ice cream cone that comes down into a point. We're not going to be able to look at individual electrons, but there's beams coming out at every height in this cone as it goes to the outside. So what we're going to do is we're going to put a force using this coil of wire. And that's going to make the electrons, instead of going straight out, it's going to make them start to move in circles. Now we won't see an individual electron doing that. But because this is cone-shaped, the ones that are farther up, closer to the top of the tube, they are going to get to travel farther before they hit the side because it's wider up there. The ones that are down towards the bottom, they're going to go in similar paths, but because the cone is closer, they're not going to get to go as far. So it's going to give us all these beams of electron together. It's going to give us a circular pattern. And that circular pattern will have the same shape as what a single beam of electrons would. So this is a pretty bad picture, and it actually is curving the way opposite the ones in our example are going to curve. But I hope it makes the point. If you've got a longer distance you can travel, like ones at the top, you're going to have more of a chance to curve. Ones at the bottom will only get to curve a little. And when we look down on this, all of those motions together will trace the path a beam of electrons would take if it could have gone the whole distance. So let's see if we can figure out anything about that curvature. So what I'm going to do is I'm now going to put my magic eye tube inside the coil, and we'll see what happens. So I've got the magic eye tube inside this coil of wire now. You can see it looks just the same with the straight sides of the two glowing regions. And that's because this coil of wire is not doing anything yet. It's not hooked up. Once I hook it up, I'm going to be able to control the amount of electricity going through with this thing, which adjusts the amount of electricity allowed through as I turn the knob. It's called a potentiometer. We'll be able to measure the amount of electricity, the amount of electrical current, using this meter, which is called an ammeter. And we're going to see electrons are affected by being in a magnetic field, which is going to exist in this coil of wire when electricity is flowing. So let's hook it up and see what happens. So just have to connect this wire. And watch the edges. As I increase the electricity, which I'm doing now, those edges start to get curvier and curvier. And that's because those electrons are having a magnetic force put on them. So I'm letting it off now. What I'm going to do is I'm going to stick this rubber rod, which is from the electrostatics experiment that we'll do later in the year. I'm going to stick it down in there, and we'll make the electrons curve to match its radius. And then we'll be able to get that radius outside of the tube. It's hard to get this lined up quite right, but I've got this rubber rod in here, and the curved edge of where the electron beam is hitting the screen has about the same radius as this rod. So we'll go measure that rod in a second, and we'll know the radius of the circle that that electron beam is being forced in. This is happening at 4.25 amperes of current, and the accelerating voltage that's sending those electrons out is 236 volts. And just to back the current off one last time so you can see how it goes back to the normal shape, letting the current down, and now removing it entirely. This device here is called a vernier caliper, and what it does is it helps us measure things that are hard to get a ruler around if we want to get diameters of things. The scales tell us the distance between those teeth. So we're going to go over to our rubber rod. We're going to stick the teeth in, and we're just going to read off that this is 1.3 centimeters. 1.25 actually.
Alright, so before I could do any calculations, I need to know the strength of the magnetic field inside that coil. So here's my equation. Although this line goes too far, B is not divided by 2. This is right here. One major source of error is PSSC type solenoids ranged in their number of turns. On average, they had 600. So I picked that as my number of turns. But I've seen 500 and there are ones with more. So that is a source of error. The current I measured directly, and the radius of the tube, in other words, from the center to the outside, I measured that directly too. So we were estimating a magnetic field inside that coil of 0.0401 Tesla.
So if we look at the path electrons are taking, it's kind of a little bit of circular motion. And in order to curve like that, we must have an inward force, which in this case is going to be a magnetic force. So that's going to be our other equation that we can use to solve for mass and velocity. So just like before when we started with a basic equation like conservation of energy, now we're going to start with Newton's second law. So the only force these electrons are experiencing is the magnetic force. Since they're moving in a circle, they have a centripetal acceleration. And now we can plug in our equation for magnetic force, which, since this velocity and force are at right angles, is just QVB. We can ignore the theta. And if we look, our two unknowns from before, mass and velocity, are here as well. So using Professor Dorothy Montgomery's method from the video we watch in class using a beam of electrons moving through a Helmholtz coil, we can just solve this system of equations to get M. So that's what we'll do next.
All right, so I simplified my two equations the best I could. There were some terms on both sides. I canceled them out. And given that the two unknowns were mass and velocity, I solved this one for velocity and plugged it into the other one. And then you continue to simplify. Ultimately, I'm left with an equation mass equals, and it involves charge, magnetic field, radius of the turn, and potential difference between the two plates. So I end up with a final mass of 2.13 times 10 to the minus 29 kilograms. That's a lot bigger than the accepted value, 9.11 times 10 to the minus 31. It's actually like more than 2,000% error. So it's not altogether the world's most successful measurement. I think error sources probably come in estimating the size of this curve, whether that rod really lined up with it. Possibly also measuring current, and also the number of turns in that solenoid. That was kind of a guess based on what I know about solenoids of that type. All in all, though, I think this is worth doing because it makes a couple basic points. Again, when we're trying to solve for relationships, it often makes sense to start with basic ideas. Conservation of energy, Newton's second law, and then look for the specifics of whatever case you're at. I also think that these are two types of equations you've been solving for a very long time. And I think it's interesting that we could put a magnetic force in here. But other than that, this is something that you learned in your mechanics course. And I think that's kind of an important point, that the guiding principles of physics stay with you, even as the problems get more and more complex. So I hope you enjoyed this experiment. I think it's really cool that we can put a force on some of the smallest pieces of the universe, like an electron. And it enters a type of motion, in this case circular motion, that's a lot like what we see in the big universe. That's not going to always happen. But in this case, the equation describing a swinging weight moving in a circle ends up being the same equation we use to calculate what was happening with an electron moving in a circle. I would be remiss if I didn't mention that this vintage piece of equipment was built in the 60s by the McAllister-Bickwell Corporation. Its instructions are long gone, but interestingly enough, it appears to still be in production in Australia by a company called Scientific and another company called Industrial Equipment and Control. So the fact that they have instructions for their apparatus was a big help, especially figuring out how to measure the radius of the path the electrons were taking by using a rod and lining up that path with the rod.